Yeah. Thanks everyone for joining. It is a real pleasure for me to introduce Dr. Vaishak Belle, who's going to give a talk titled Tractable Probabilistic Models for Ethical in Causal AI. I think, well, he has a very extensive and well-known background in the science and technology of AI, with widely published articles and giving talks at prestigious venues. And at the moment, he's the Chancellor Fellow and reader at the School of Informatics at Edinburgh. And he's also an Alan Turing Institute Faculty Fellow, Royal Society University Research Fellow, and a member of the RSE. He also directs a research lab on AI, the unification of logic and machine learning, and with a recent emphasis on explainability and ethics. And very much looking forward to his way, how he explores the ethical dimensions of machine learning technology and give us some insight and input regarding those concerns of interpretability, bias, and responsibility issues. So the floor is yours. Questions can be put in the chat or asked afterwards, and yeah.
Thanks very much, Daria. Hi, everybody. I see a bunch of Edinburgh names, so I guess I could potentially have given a bit of the talk here and broadcasted it. Anyway, thanks for joining in today. So this is, as the title indicates, it's a research agenda slash position paper of sorts. So I suspect there'll be lots to disagree with, but bear with me, because I think at the core of this there is an idea which at least in the last couple of months has kind of convinced me that there is a core computational abstraction that is really useful for the challenges of ethical AI. Okay, so what's on for today? I'm going to very briefly motivate the need for integrating logic and learning for ethical AI. I think it's fairly common nowadays to see machine learning taking on ethical AI in terms of definitions of fairness, debiasing, and whatnot. But I'll try and argue that there is a need for high-level representations. For those of you working in high-level representations, this should be kind of obvious, but it still might be useful to know about it. I'll introduce one candidate framework for this integration. These are circuits and or graphs. Maybe you've heard of them, maybe you haven't, but you'll see the connection hopefully through this talk. I'll explore how these circuits, we've done some work on fairness, moral responsibility, causality, constraints, explanations. We're not the only ones. There's a whole sub-community of machine learning dedicated to applying circuits to various problems in machine learning. So this is an area to watch out for. And I will point out, and again, this goes back to my point at the start of this talk, that there's a long road ahead. And I'm not arguing in this talk that we have accomplished anything in the broader picture. As Daria mentioned, feel free to put your questions in the chat. I suspect I won't see them, but Daria can just speak up and let me know if there are questions. Okay, so this is just a bit of background. We know that machine learning is being used for a lot of different applications. Some of them are fairly innocent, book recommendations. But then you go on to things like risk analysis and insurance pricing in self-driving cars and surgeons. It suddenly starts becoming important to appreciate the critical nature of the decisions taken by the systems. And there are many ethical dimensions, right? So there is things like privacy, but I would say in the long term, what we really care about is the idea that we want to allow for morally permissible actions. And this, again, is debatable what exactly this amounts to in an automated system context, but let's just take it for now, that we need a way to understand what morally permissible means, either as a human expert looking at the system or potentially the system itself, if there's some way for it to evaluate certain consequences. Things like fairness, blame, accountability, explainability are all aspects that play into this picture. Nothing new here. What I guess we have to also appreciate, especially in the context of our UKRI node, is that there are many definitions in literature, but one of the reasons we did, this proposal does make sense, is to notice that there's a lot of debate if a formal approach is even the right thing to do here, and we recognize that there are numerous challenges in model building. So this is everything from data collection to ascribing responsibility to the right party, to understand how data labeling happens. So these can, amplify abuse of power and privilege. And this is something we recognize when we think about machine learning in the wider world, especially with language models and so on. Okay. Some people now argue that let's do human in the loop. But again, there's quite a lot of discussion here that we don't quite have a precise way to identify where is the boundary between delegation to a human being versus automated decisions. So, we don't quite know exactly how to articulate this boundary, and that kind of raises a challenge, because then the easy thing to do is to wave your hands and say, oh, everything, there's a difficult situation, let's just pass it on to a human being, but it doesn't quite work, right? Delegating actions to human beings is not easy, especially when they're quite time-critical decisions to take, and sometimes you have ramifications of action, so you can have long-term effects that are quite hard to predict at the moment. So I really think that, and this is an argument made by lawyers and regulators as well, that in some sense, you do need some interface where there is a system that can provide the right amount of information. And the way I'm interpreting this is that we need to have a system that is able to reason about its actions. And this is, again, broadly construed. In the case of a prediction system, you could imagine the actions being, do I approve a loan or deny a loan? But if you want to think about something far more complex, you imagine like a logistics scenario where you have a whole series of actions that you can take. Then you need to think about the long-term consequences of these actions, and you need to have a picture of these of the space. And again, this is not to those of us working in automated planning in AI, this is not a completely new thing, but in the context of, I think, ethical and responsible AI, this needs to be appreciated, because much of the discussion in the literature happens to do with one-shot prediction models, and not really these broader systems where there's a series of actions taking place, and there is some scope to really have an overview of the information exchange between the human being and the system. Okay, so and again, keep in mind that if you consider a machine learning system, understanding the model's rationale itself is challenging, again, going back to things like explainability. So there are a number of different challenges here, but ultimately the point I want to make here is that we do need systems that can think about their actions and the effects of these actions. This can be anything from the standard causality literature, thinking about causal attribution. It can be about automated planning systems, thinking about long-term effects. So there's a whole range of options here, but we do need systems who have some account of the actions that they take. Okay, we need to provide a framework where we can delineate which parts can be automated and which parts can be delegated, and we need to understand how these systems, and when they're deployed in an environment, what kind of assumptions are made, what awareness is available for these machines about their wider environment, and these kinds of context and settings need to be understood thoroughly, both from a regulatory aspect, which I guess is the main thing that we often hear about in law, but as computer scientists, we need to think carefully about the assumptions going in when we build these systems. So in light of that argument, the position I'm taking in this slide deck and a series of papers that I've been thinking about is that perhaps we need to have a two-pronged approach. Okay, so on the one side, we should be looking at philosophical notions from formal epistemology, things like beliefs, desires, intentions, but also combinations of that and what happens in knowledge representation, where you have ontologies for space, time abstraction and causality. And we have to keep in mind, again, that the limitation of these approaches is that it's kind of an idealized perspective of epistemology grounded in some agent's mental state, right? So this is all the information that the agent has, and it's trying to reason about these actions. Now, this is on the one side where you draw on this rich philosophy, but I think the way that this can be grounded in concrete context that we find the kind of applications we're interested in is by thinking about knowledge acquisition. How do we convert or how do we go from observations about the real world, which could be anything from sensory observations to interactions with other human beings? How do we go from this information to the knowledge that is in the system? So often in this community, especially formal epistemology, you often find that there is not much of a discussion on knowledge acquisition, at least in terms of conventional machine learning. Okay, so there is a gap there. The community has done a lot of work in trying to provide a formal model for these kinds of notions, including beliefs of multiple agents, but not much really about acquisition. And that's perhaps a problem that we want to address here, that to bring together these high-level concepts and low-level observational data, we need to think about the bridge, and we need to think about the bridge carefully, because concepts that we acquire from low-level observations will translate to the language we use when we communicate and write our models for these agents, okay? And again, if you keep this spectrum in mind, there's a long-standing problem that we know in knowledge representation, that there is an expressive complexity trade-off. For instance, even if you think about propositional reasoning, we know that it's NP-hard. So we have to deal with this complexity trade-off on the one hand. We have to deal with the expressiveness on the other, and we have to deal with knowledge acquisition the third, okay? So there is a kind of, if you agree with me so far, in the larger ecosystem where we need interactions between automated systems and humans, there are these three components that we need to make peace with, right? The complexity, the expressiveness, and reasoning about high-level mental concepts, and acquisition, okay? Now, we know, for instance, that there are areas that actually do come very close to this picture. For instance, it is widely recognized, at least for the last 20 years, I would say, that although machine learning is fantastic in a number of tasks, it is in a very, very narrowly scoped context of predicting future instances based on past observations, when the data is fairly structured in terms of labeled samples. As soon as you want to talk about deduction, when you want to talk about reasoning, you think about the kinds of visual question answering tasks that you often find in language models these days. It really makes sense to think about, relational structure, adding some domain context. You might want to reduce the training effort of machine learning models by incorporating some kind of domain knowledge. So we recognize that there is a need to integrate these two fields. This is not something that's new. What is new, as I said, is really trying to address this with the concrete context of trying to balance high-level concepts, especially mental concepts, with knowledge acquisition. So the main thesis that I want to advocate here is very simple. It basically says that we need to think about tractable probabilistic models, and I'll come to what these are in a second. Two problems in ethical AI, okay? Current evidence, at least if you look at the machine learning literature, is that they're quite attractive for jointly addressing three problems. For reasoning about possible worlds, so probability distributions, intention models, desire models, ranking functions, etc., etc. They're quite attractive for reasoning about possible worlds. So this is exactly what you would need in logics of knowledge and intentions and norms, right? Second, they're tractable, which means that, and I'll again explain what this means. And I would argue tractability is something we need to care about if you want to talk about real-time behavior and scalability. And finally, they are tackling the problem of knowledge acquisition as considered by the machine learning community, and they're fairly competitive on a number of tasks. Okay, so these structures are basically hitting three spots that I think we need to be thinking about when targeting ethical AI, which is what they are one nice candidate. And I'll try to sharpen this argument as we go through the rest of the slides to see exactly how this evidence comes about. Okay, what I'll cover is I'll talk about these circuits. I'll talk about fairness, causality, and counterfactuals, and I'll try to see how much I can do in the given time. There's no need that I need to wrap everything up, as long as you get the main thrust of the connection between these models and the overall thesis. I think I would be generally happy with the content. So Daria, if you feel that we need to give some time for questions at the end, feel free to stop me and I can wrap up. I'll make a very quick point, why this is different from existing approaches to knowledge-enhanced ML. So knowledge-enhanced ML is broadly the area I'm calling things like loss function adaptation, where in neurosymbolic AI, things like using constraints in language models, statistical relational learning. So what are the differences to this? Oops, not sure what's happening. I think it's frozen. Okay. So what are the differences to this area? As I mentioned, there's a long-standing argument for connecting logic and learning, but primarily I would argue that these are for improving machine learning models or competing with machine learning models with respect to domain knowledge. Okay, so what I think we need to do is to pay serious attention to actions, ethical concepts, norms, causality, explanations, mental modeling, and agency. And there are approaches right now. For instance, if you look at explainable planning, which is an area of research where they try to apply explainability in understanding what plans need to be achieved, there is a bit of mental modeling. So people are taking this up seriously, but the key argument I would make is that what differs this research agenda from the existing one is that we need to pay attention to these notions fairly seriously. And as I said, the results here do not take all such steps. I will simply provide an argument for probabilistic tractable models and their promise, but how they can be extended for more expressive languages remains to be seen. But given that they are exciting and important candidates for tractable reasoning or possible worlds, I imagine that they might be a key player as we go up in terms of expressiveness to languages with mental notions. Okay. Just to wrap up the first part of this talk, let me again reiterate that this is making a very strong argument, but at the same time, it's making a strong assumption as well, in the sense that computational solutions do make lots of assumptions about the environment. These are not appropriate, as we have seen, and that is precisely the kinds of problems we try to address in this node, about the lack of computational solutions being a one-size-fits-all for deeper challenges in deployment. And there are multiple opportunities, as we know, with machine learning for failure and misspecification, including data collection. And if the recent debates and the discussions on Twitter about the bias of face recognition models is an indication, this is a big problem. And this is also true in language models, right? Like the foundation models that Stanford likes to refer to. So orchestrating a framework, where there's a kind of flow of information from the computational abstraction to the human being and then to regulation is not an easy challenge, and that's precisely what we are concerned with in this node. Okay, all I think is that implementing these formal notions is a small step, but we have to keep in mind that in analysis in fairness literature, for instance, has shown that the existing definitions of fairness are mutually inconsistent with each other. So it's not even clear that the definitions we come up with are good enough, right? An agenda such as the one I've identified here is completely orthogonal to this broader picture. Okay. The suggestion we only make is that by building these kinds of models, perhaps we can have some clarity and better control on exactly the kind of decision making that happens in these systems in a kind of transparent manner. So that's the only argument we're making, and that by addressing knowledge acquisition with epistemological notions, we might have a better sense of how we might capture the information states of these systems. So that's the only thing we're doing. We're not suggesting a solution to the bigger problem. Here's a very rough picture of where things fit. So on the left-hand side, you see the standard area of knowledge-enhanced machine learning, where you have machine learning. That's the orange circle, and the reasoning and background knowledge is the blue circle. So that's on the left-hand side. Neurosymbolic AI, I would say, is the top right, where you have reasoning and background knowledge with deep learning. So these are things like neural theorem provers. The area existing right now in terms of tractable learning is on the second row left-hand side, where reasoning and background knowledge is combined with knowledge acquisition and tractability, a concept that I will make precise in the slides that come. The work that I talk about in this slide and some other work that's happening at the same time is on the second row right-hand side, where you have notions of some notions of causality, some concepts of ethical norms combined with learning and tractability. And perhaps what we really need is on the bottom, which is the second row right plus norms. So we need notions of norms, multi-agent beliefs combined with learning. Okay, so this is just to schematically represent where we are in terms of this progress. And this, again, as I said, is completely orthogonal from the broader dimension of delineation and understanding where the boundary lies between automation and passing the control back to the human. I'll go into the key challenges. I was wondering if there are any questions. If there aren't, I'm happy to go on and you can ask towards the end.
Didn't see anything in the chat yet. So
that's no problem. So what are the key challenges for this research area? Okay, so there are some things that we already know from knowledge enhanced machine learning, and these are hard questions to answer. This goes back to, do we learn with a blank slate versus do we have some kind of hard-coded knowledge that helps us acquire some bootstrapped that we can bootstrap on? Okay, so these are classic questions in knowledge enhanced machine learning. What is a knowledge, what is known in advance versus what can be acquired in observations? How do we generalize from low-level observations to high-level concepts? So these are classic questions. What I think is different here is specifically thinking in terms of what environment actor model is needed for the formalization. Now, keep in mind that on the environment side, we might want to allow for concepts such as time and space, controllable versus uncontrollable variables. On the actor side, we might want to talk about knowledge, beliefs, intentions, communications, and social cues. So this is the kind of added dimension to the existing knowledge-enhanced machine learning. Likewise, if you think about formal principles that need to be embedded in the system, what is expert knowledge in terms of the training? For instance, you might say that in the case of fairness, you might want to guarantee that all predictions are completely irrelevant on the gender. So this is the kind of expert knowledge that's added to the training. You can contrast that with some kind of ontological knowledge that needs to be respected with respect to all the properties that the system obeys. So for instance, the laws of gravity, if you're training a deep learning system to give you some predictions about physics, okay? And again, here you see, how robust do we want these predictions to be? Like, do we want these background knowledge aspects to be hold always, or is it fine if there's some amount of failure there, right? So there are many other challenges like this, okay? I'll skip over some of these, but they will come up in what I present. So I have some slides on some examples of logic, probability, and learning. I won't go into them in too much detail, mainly because that's not quite the focus of the talk. As I mentioned, tractable models is what I want to hope to convince you about. But I'll run through these slides. Feel free to stop me if I'm going too fast, but I'm not expecting you to really follow every detail. I just want to give an illustration of the different dimensions we find ourselves in this space, okay? So a classic, example, and this is something, even people in informatics like Ian Simpson work on, are knowledge graphs. And these knowledge graphs are basically computational graphs where you have, in this case, you have proteins interacting with various genes, right? The key property here is that there are some probabilities attached to each of these edges. And the idea is that with a graph like this, you might be interested in various probabilistic computations. Okay, things like, is a gene involved in a disease X? What is the probability of involvement? What are the subgraphs needed? For instance, some of the research that Ian Simpson has done has focused on identifying certain genes that are reflected in both autism as well as bipolar disorders, right? So these are the kinds of things you can do. You can query these graphs. Now, notice that these graphs obviously are basically can be represented in logic. They're in fact probabilistic logical formulas, but you obviously use machine learning in terms of extracting these graphs and querying them based on the data you might have collected, okay? So this is an example. Here's another example from the medical domain. Here again, you are basically trying to predict the probability that somebody might be, of risk for things like diabetes, but as opposed to classical classical prediction, what is happening here is that you have fairly complex relational data. Okay, so you have patients with various genders. Obviously, there are various diagnoses, and this might be a longitudinal study. Okay, so you might have collected data about things like blood glucose across many years. And in that case, the kind of query you might be interested in, which is on the right-hand side here, is what is the probability that some person is at risk, given that they're male, given that in the year 7, the 7th year of the longitudinal study, their age fell between certain gaps and the cholesterol levels were between certain numbers. Okay, so this is a fairly complex query. And for those of you working in machine learning, you would see that it's not quite easy to formulate such queries in most machine learning models. Okay. Here's another example where, again, you have two equivalent ways of representing probabilistic information. What you're trying to capture here is that friends influence each other to smoke, okay? And on the right-hand side, you have a fairly complex Markov network, so each of these nodes are random variables. And on the left-hand side here, you have two formulas. If you're familiar with logic, this basically says that if X is a smoker and X and Y are friends, then Y is a smoker. And if X is a smoker, X cuffs, okay? So basically these two formulas instantiate this graph, vice versa. But the interesting thing in the logical aspect is that you can add new knowledge, okay? So suppose I wanted to now add that family members also influence each other to smoke. If I had to go back to the graph and tinker with it, it would be quite an arduous task. But it's fairly easy to add logical knowledge of this sort. This is, in fact, a program, and this program is much more involved. But I thought this program is a nice addition to talk about the situation we found ourselves in the last 2 years with COVID. Okay, basically here it's saying that there are two individuals, A and B, that a randomly chosen person being patient 0. There's a 0.1 probability attached to that. And two randomly chosen people, the likelihood of them being in contact with each other is 0.1. Okay, and then I might say that if you are patient 0, then you're infected, and if you're infected and you're in contact with somebody, that person is infected too, with a probability of 0.6. Okay. To write this down and work it out by hand, it will take you a bit of time depending on how well you're familiar with the laws of probability. But okay, this is a program that can be used on this website online, and you'd get the numbers. Okay, so that's the point I want to make, is that this program is quite readable. Now, let's assume that I came back to you and said, you know what, the contact and the infection spreading a rule, I don't want it to be probabilistic anymore. I want it to be deterministic. If I said that to you, you'd get quite annoyed. Go back to your sheets and try to work out what the new numbers are. But in the program, it's simply a question of dropping that probability. Okay, and so in all of these cases, you have symbolic structure or logical structure with certain probabilistic semantics that allows you to compute interesting things that are hard to define using standard machine learning models or standard graphical models, because of how awkward and complicated these rules can get. Okay. Continuing this example, let's say that I also wanted to add that a randomly chosen person might have gone to a risky place. And if a person has gone to a risky place, they're also likely to be infected. So there are two different sources for infection. Either you got in contact with patient 0, who got in contact with somebody else, who perhaps got in contact, or you got in contact with somebody else who got in contact with patient 0, et cetera, or you went to a risky venue. And so there are two ways of getting infected. Again, this complicates the model and so on and so forth. I can add susceptible people to this group and make it even more complicated. We've also applied this to things like language. So this is a question you often see in a GCSE type tests, right? So you roll a die, twice, and the first time it gives you a certain number. What happens? What's the likelihood that it shows you the same number again? And we can show that it can be mapped to these kinds of programs, and you can compute these answers. Okay. What I want to say here is
7 more minutes, so there's also time for questions.
Sure.
For the top?
Yeah.
So
yeah. What I want to say here is that they're basically two sides of the same coin. Okay. So all of these different representations, basically they can be converted to what is called as weighted model counting, which is basically a kind of extension to SAT solving. Interestingly, once you convert them to one of these problems, you can represent these as and/or graphs. Okay, and these and/or graphs have certain properties such that once you obtain them, you can compute probabilities by doing a pass over these graphs. Okay, so there's no free lunch. So the problem here is that in converting these problems to these graphs, it might take exponential time. But once you have these circuits, inference is linear. In the case of a Bayesian network, for instance, this is a network on the left-hand side. This is the same program on the right-hand side. It gets written up as these rules. No need to go through them, but you can take my word for it that these can be then converted to one of these and/or graphs, and the probability can be computed. Now we can go back from the other way, right? So this was from the logic to the circuit. It turns out there is a way to represent distributions that also has a logical flavor, okay? So just to see a simple example, imagine you have a random variable with the probability P of success, okay? You could represent it using an equation like this, which says that P of x plus 1 minus P of x bar, where x bar is false, okay? And the idea here is that as you extend this to more variables, it has a product structure and a sum structure, which is precisely the and/or graphs that I talk about. So there is an efficient way to encode distributions that leads to this and/or structure, or you can take one of these logical models and get an and/or structure. So there's a deep connection between the probabilistic models on the one side and the encoding of high-level representations on the other side. So this goes back to my point to say that current evidence suggests that these models are really good candidates for representing probabilities, for reasoning about possible worlds, and a knowledge acquisition. Okay, so you can learn these structures. In fact, they lead to a kind of deep learning where instead of the sigmoid functions internally, you have ands and ors, or pluses and or products and sums. Okay, different ways of looking at the same structure essentially. Shall I try to wrap up by 2:45, Daria?
Yes, that would be good. Yeah.
Yeah. Okay, so what does all of this have to do with ethics? I'll have to speed up a bit here. What I want to, so I hope with this you kind of saw that these tractable probabilistic models are a nice candidate, and they provide a deep connection between rich probabilistic logical languages and possible worlds. Okay, what I'll quickly show is that how these models have now been used for various problems in ethical AI, and again in the space of computational solutions. Okay. So I have to really, zip through these. So I apologize if in the flurry of changing slides, it gets slightly taxing to follow through. But maybe I can skip one or two of these concepts. But for instance, in the concept of fairness, what we have basically showed is that maybe what I can do is do it this way so that I don't have to. So what we basically showed in the concept of fairness is that typically, in fairness, what we can care about is the fact that you try to obtain predictions such that a gender bias, race bias, and other things don't pop up. And these can be collectively lumped together as protected attributes. So typically what you're looking for is a machine learning model that is trained on X prime, where X are the original features, and you remove the contribution of these protected attributes, right? So essentially, if it's gender or race or ethnicity, you don't want it contributing to the feature space that you train the model on. Now, obviously, this is a hard thing to compute, okay? So here's where you can use tractable models, for instance, to basically compute this expectation and eliminate or de-bias the model. So you can either do this before training the model, so you can completely remove the predicted attributes, or you can train the model and then remove the contribution of these protected variables. So this essentially allows you to mitigate concerns about, correlation popping up. And we show that, we get fairly conclusive results that these techniques perform very well, and they're fairly quick, okay? Likewise, another kind of problem we've been thinking about is what would it mean to embed prior knowledge into these models? So the setting, for instance, that we might consider is the trolley problem, the infamous trolley problem, which I assume everybody hates now. But nonetheless, this is a case where you have, some possible effects, some possible consequences, and you want to choose an action that minimizes these consequences broadly construed. So there was one framework that recently came out on how exactly you could model these kinds of scenarios. These are based on structural equations. Okay, so structural equations are kind of mathematical equations which help you identify how the effect of certain actions affects certain variables inside the system. And we were able to show that provided you give the structural equations for such domains, not just the trolley problem, we also studied some kidney exchange problems and a bunch of other domains. What you can do is you can take these structural equations, okay, you can construct the tractable probabilistic model from these equations, and you can learn the probability of response from data. Okay, so again, I apologize for it being quick, but I'm hoping the point is still made, that we were able to study this and trying to see how well it predicts aggregated preferences in the trolley problem and a bunch of other problems, and we were able to show that the model does fairly well. Now, let me provide a caveat here in that aggregated preferences have been known to be problematic because they might, in some sense, average out the preferences across cultures and genders and so on. So again, this is to indicate that we don't really have a solid solution to this problem of ethical dilemmas, but we can model some notion of reasoning about actions and consequences using these approaches and learn them from data. I'll skip over the last bit of the talk, but I wanted to quickly say that we have a bunch of results that essentially shows that if you have prior knowledge, such as make sure that the prediction never harmfully acts on one gender versus another, or you can basically incorporate such a constraint in the model itself before the training happens. Okay, so we have done a lot of work on trying to understand how these constraints can be embedded. How can we extract explanations? And in fact, this is not simply an application of the technique. We're able to show that there is something very fundamental. As a simple example, there is a very popular explanation technique called as counterfactual explanations, which are quite popular in law. Okay, basically the idea is that if you have a prediction that somebody was denied a loan, a counterfactual would say, well, had this person's salary been 10,000 more, we would have approved the loan. Okay, and these are obviously popular because they provide a very intuitive way for you to extract an explanation for the model. We were able to show that, in fact, when you want to extract counterfactual explanations for things like decision trees, Bayesian networks, and random forests, there is a very fundamental way in which you can represent these things as and/or graphs and pose the counterfactual directly in terms of these and/or graphs. Okay, so what I'm trying to say is that it is not simply a question that we take a hammer and whack it against a nail, but there seems to be something very fundamental here in that as soon as you start looking at some of these problems, which force you to consider a number of possible scenarios, a kind of organic way to both reason as well as learn from data regarding such searches turns out to be tractable probabilistic models. So they are, I think, a very interesting candidate for this research agenda. Okay. Let me wrap up. So, as I said, the key point I want to pass on here is that tractable probabilistic models are important for possible worlds in tractable computation and knowledge acquisition. This is very much in the early years. There's a whole bunch of interesting work right now on trying to capture fairly interesting ethical ideas such as consequentialist versus deontological ethics in epistemic logic. So I'm hoping that there might be a way to go from these logics to these tractable models, okay? And the results that I discuss here are basically occupying a spectrum in terms of what we can accomplish. Let me stop here because I have a few more points to make, but there is a longer version of an article based on the talk that I'm happy to share, which kind of wraps up this argument with a bit more detail. Thanks again for listening, and sorry for rushing through the technical meat of the talk, but I wanted to make sure I wasn't misunderstood regarding my intentions.
Thank you. Just checking the chat. Are there any questions? Oh yes, I have one raised hand. Craig?
Hi, can you hear me?
Yep.
Yeah.
Hi, thanks for the talk, Vaishak. I've got to say, as a sort of position paper, I've often been pretty tempted by these tractable models as well, like some product networks and stuff, because you get, the interpretability and the query speed and things for free. But often when I have like a complex ML system, it's usually because there's some bottleneck component that I need one of these crazy deep networks for, or like I have an extremely high dimensional image or speech data or something like that I need to push through this uninterpretable model where I can't get the interpretability for free. So I guess I'm wondering, where do you see the kind of tractable model way of doing things fitting into a system where you have this black box bottleneck that you can't crack open because of the sensor input?
Yeah, that's a great question, Craig. In fact, I tried to articulate this in the position paper. So there are two ways to look at it, right? So you can take the approach that I want one language for one ring for them all, right? One size fits all approach, which is to say that whatever problem I encounter, I'm going to use TPMs, right? That's not quite the position that I take. I think it's an interesting idea. Perhaps it would help us better understand a way to do computational abstractions in different domains. The way I see it is that so let's say you take one of these, as you say, you use deep learning to do image recognition or some other complex image or language task, right? There are approaches, as you know, like deep problog that on the one hand allow you to combine the outputs of deep neural networks with logical knowledge, and things that you have worked on as well with RAM, for instance, where you have tried to train the output of a neural network by using loss constraints based on logical models, right? So I see them kind of fitting in the same space in the sense that they don't yet seem to, at least the some of these approaches don't necessarily apply TPMs. But if you go down the problog route, the argument is that it does in the end need you to require about possible worlds, right? Even if the deep learning system itself and its output is its own thing, once you pass this output and you reason about this, it requires you to reason with possible worlds. And that's where I think the tractable model approach is actually useful. I'm not saying it needs to be done, but I think in any domain where there is a bit of reasoning, even if a large chunk of it can be solved using deep learning, that's great, right? If the guarantees provided by deep learning are fine for you in that specific context, there's no reason to necessarily be dogmatic about it and suggest that let's replace it with something else. I think that once you go beyond that output and connect these outputs to other concepts, you start to think about, how do these concepts connect? How can I consider the effects of these outputs? And ultimately, you stumble on the problem of wanting to reason about the environment. And again, you could also use a thing like NDP, right? So that's also not, I would say, completely divorced from this argument. But in so much as you need to reason about possible worlds, TPMs are an attractive candidate. Whether they are not the only candidate, so you could think more broadly about it too. I don't know if this kind of answers your question, but just to say that it's not really meant as a one-size-fits-all. It's more the question that, recognizing that a complex automated system nowadays has to deal with, the mental states of different agents, has to reason about information flow, and all of this requires some sophisticated reasoning for which we know that TPMs are good candidates.
Cool, thanks. Yeah, that helps actually.
Any further hands? I was wondering because well, I'm not from the domain, so my question might be a bit. But I'm actually interested in the question of specifically blame, and that approach is very interesting. That so my question is, considering that those systems basically blur the line between the kind of world you try to model, how do you establish that kind of blame with a certain actor responsible for malfunctions, for example, where those malfunctions cannot be easily seen from the outset, and those kind of errors through operation? So how do you distribute that kind of alternative scenarios in a big uncertainty? So that is something that I was wondering, especially from a legal perspective.
But you're absolutely right. So there is not an easy answer to it. So on the one hand, there are opportunities to at least say that there are things that the agent is uncertain about, and there are ways to capture that uncertainty. But again, in a very quantitative setting. So basically, you would have to predefine the set of actions that potentially impact, and then you could say, okay, I could imagine that doing this may cause this or that, and there's some uncertainty regarding that, right? So you can capture things like that. It doesn't quite give you the tool to really do more broad level, how do you call it, broad level misspecification queries, right? So if it is a case that, yeah, as you say, there are some components that that lead to certain actions not being triggered, which aren't quite captured in the model, then basically you have a model that doesn't function, doesn't do its job well. But it's perhaps not the model itself to blame, but then maybe the modeler only can deal with so much. Maybe the modeler would find it hard to really come up with all the different scenarios in which the misspecification can happen. And that's why the regulation argument is the regulation side of it is so important, right? It's not, I don't think there is any, at least, in the last, in all the history of AI, we haven't quite really found a way to go beyond this, all the possible specifications of effects, right? So we always have to, in some sense, call it quits and say, this is what we can model. And beyond that, we're now getting needlessly complex, which is hard to track. But we can try to make the model as good as possible. And the way to do this would potentially be to run some simulations where you can have actual feedback with stakeholders that can go and criticize some of the actions taken, right? So this is something that we can hope to do.
Right. Yeah. Thank you. Any further, like, we still have time for one more question. Or in the chat if it's easier. Yes, Bhargavi raised her hand.
Hi, can you hear me?
Yep.
Yeah.
Okay, great. So my question is about, you briefly touched on the idea that you might be able to, before training the model, do some sort of controls and exclude certain variables that you think might be biasing the, or causing some sort of bias. So I was wondering if you could expand upon that a little bit, because in some of the work that I've read, I've sort of seen this idea that even if you remove variables, you're still going to learn certain attributes through the correlation effect. So I was curious how this would bypass that issue.
Yeah, that's something that okay. So there are two aspects to it. So there's one aspect of identifying all correlations. This is something that can be done, right? So essentially, I mean, to a statistical degree. So you can kind of go in and find all strongly correlated and weakly correlated. An example might be, let's say your gender is hidden, but nonetheless the school you go to is very strongly indicative that you're female, for instance. You can pick up on that if you have the context to pick it up, right? So provided you have the necessary concepts that provide the associated information, you can provide statistical tests that pick up these correlations. You can remove the contribution of all of those such correlations and train the model just on that. But what this doesn't do is tell you about systematic issues in the system. An example is, let's say, for instance, I decide to pay all female employees in a company lesser than male employees. But nowhere do I record their gender or ethnicity, right? And there is nothing from perhaps the name, but let's say I also remove the name. There is nothing to indicate, at the face of it, that there is discrimination against women. But there is, but so the statistical test will figure out, will will show you or not show you that there are any correlations between gender and salary, but this is clearly a systemic bias. So the way to fix it, one possible thing you could do is something that I've been looking into, is this idea of having an equitable constraint. So you would basically find a way to see if all groups of people universally seem to have some property that is different from the other group, right? And maybe this could be helpful as a test to identify these things. But I don't know. I don't think there is a solution in the literature either, right? About a categorical solution to this. These are just things that, it's also true for counterfactuals, right? So counterfactuals as well, they're very attractive in terms of being simple, but sometimes they can say, if you get an LSAT score of this much, you will certainly get into this university, but they might not recognize that there might be other factors for low LSAT scores, et cetera, right? So, not an easy problem to solve. So all you can do is find ways to go through the argument, see if there are systematic reasons why certain groups are discriminated against, and then find a way to resolve it. But I don't think it's a purely data solution. You need to do something else, right?
A quick follow-up is just around, like Craig had asked about the issue of, you had mentioned maybe you don't need to be dogmatic about requiring these sorts of reasoning techniques, but my question is about, if you think about from a perspective of, like, say, a regulator or someone who is trying to be an overseeing body, how then would they be able to understand the potential system attributes and potential risks of a given system?
Yeah, that's a good point. I think at this stage, there isn't quite something that we can really say on that regard, except to suggest, so if you take one step up, so rather than focusing the argument on tractable probabilistic models, if you focus on formal models of knowledge and belief and how they connect to various things, I suppose there it is possible to provide some notion that this is the information that the system has, this is what it expects, or this is what entails from that knowledge, and based on that, it arrived at this decision, right? So this is a level of clarity that current machine learning systems don't provide, right? It's not simply a question of saying this is a decision boundary. You're going one step ahead and saying, this is my world model. My world model consists of saying there are X humans, et cetera, and from this world model, I conclude that this is a permissible action, and therefore I suggested this action, right? So there, I think it does provide a level of clarity. What I don't know yet is, what is this interface that can communicate this information to the regulator, right? So what does it look like to say, this is my information package, as you will, this is what I know, this is why I acted this way, what is my justification? So it's kind of like an explanation, but really the old-fashioned notion of an explanation where you construct a kind of a rigorous chain of thinking to tell you why you concluded something. So that's a level of clarity I think that current machine learning systems don't have, and which could be useful to a regulator.
Right. Thank you so much. And thanks for the questions of the audience. And if there's if there's any more questions, I guess I can write you an email. And having said that, a round of applause, virtual applause. And yes, thank you.
Thanks everybody for attending.
Yeah.
Bye.
Bye.